Hello and welcome to Lecture 70 of my course From Data to Decisions. I'm Chris Mack, your instructor, and this is our lecture on factorial design, one of the series of topics we're covering in the overall topic of design of experiments. Here we're going to use R to do some creation of a factorial design and analysis of data from a factorial design. As always, the R script that we are using in this lecture is available on the course website. So you've hopefully already listened to the lecture on factorial design, previous lectures in this course. And the first thing you want to do when doing any kind of design of experiments is, in fact, do the design, right? There's two steps. We design our experiment, we carry it out, and then, well, two analysis steps, designing and then carrying it out, and then finally analyzing the data that was generated by the experiment. So there are some fairly simple rules for simpler factorial designs that we can use, a full factorial design or a half factorial design. There are some more complicated designs possible, especially if you don't quite have enough data to create a full design, or if you want to do, say, a quarter design or something like this. Rather than memorizing or learning all of these rules, maybe an easier way to go is simply to use a piece of software that can generate designs for you. I think out in the world of industry, the most popular piece of software for doing design of experiments is JMP, JMP from SAS. But we're going to use R, which is also quite popular, one reason being that it is free and open source. So how do we design? How do we create our designs for a factorial design? Well, as you might expect, there's a couple of different packages out there in R that can do that. Here I'll use one called AGL Design. I've already installed it, so now I'll just load the library. They have a function called gen.factorial, which generates the factorial design. You tell it number of variables and vars, 3 in this case for our example. That's 3 factors. And then for each factor, there's a certain number of levels. So what are the levels? Well, I'm going to say the first variable has 3 levels, the second variable has 2, and the third variable has 3. It's just an example. If I set center equal to true, then I have a symmetric design where the levels are labeled as -1, 0, and 1, for example. And then I can supply variable names. Factors, I just call them F1, F2, and F3. All right. So when I run that, it prints out here in the console that design. So we see that we're going to run 18 experiments, which is 3 times 2 times 3, but full combination, plus replicates if we do any replicates. I can output this into a data frame. That's the output of gen.factorial. And then I have everything set up to where all I have to do is, when I make the measurements, to add another column of the measured results, or multiple columns if I have replicates. All right, here's another simple example, just a plain old 2k design, 2 to the k design. So the levels equal 2, number of variables equals 3. If I run that, I can output the results to this data frame called DAT here. And if I print out that DAT, the data frame, I see the conventional 8 experiments required for a 2 to the 3 full factorial design, 2 levels. This might be the kind of thing we use for a screening experiment. All right, so once you have your design, you go out, run your experiments, you fill in a last column with the actual numbers you got from your measurements in your experiment, and you're ready to do some analysis. So let's go down a little further in this file, and we see that I have put together a factorial design.csv file with some results that I took out of this classic textbook on experimental design by Box, Hunter, and Hunter, Statistics for Experimenters. That happens to be the textbook I used when I was in college and took a class on experimental design, and it's still one of the best textbooks out there, although there's certainly a lot more as well. So I will load this up into a data frame called yield. Let's take a look at what that is. So yield is a simple table. It's got 8 runs. It is if you look at the results, you'll see it's a 2 to the third full factorial design. For every yield is the output. Temperature, you see there's only 2 values, 160 and 180 in degrees C. Concentration, percent concentration, also only 2 values, 20% and 40%, concentration of some material. And then catalyst, I have 2 different kinds of catalysts, so there's an indicator variable 0 or 1, and what type of catalyst I used. And then the yield is the percent yield of production of the chemical that I'm trying to achieve in this manufacturing process. And the idea here is to maximize the yield. So that's our data. Notice that I have this column called run, which I don't really need. So the first thing I'm going to do is remove column 1 by using yield -1 to remove column 1. And when I look at it now, I see, oh, it's gone. Now I only have the actual data. Also, this catalyst is either a 0 or a 1, but those are just numbers in the file that I read in. What I want to do is turn it into factors. And that way I can do, as these are factors, use this as an indicator variable in my analysis. So to do that, I use this factor command. It will take variable yield $catalyst, turn it into a factor, then I'll stick it back right into yield $catalyst. When I do that, I can't see any difference when looking at the data, but internally, now R knows that this is a factor rather than a numerical value. Well, as always, one of the first things you want to do when you look at data is to plot it up and see what you can intuit about the data before you do any statistics. When you have multiple regression variables, it gets very complicated to plot things up. And it's especially true for factorial designs because you don't necessarily have a dense array of values within a particular predictor variable. Sometimes we only have 2, as in this data set. That can be a little bit difficult to look at the graph and see what's going on. Nonetheless, we can do the standard plot, which gives us these kinds of plots. And because it's only 2 levels for each factor, again, not necessarily easy to see what's going on. But these marginal plots are really, with yield as the output, is really the most important thing. So we have yield along the y-axis, and then here, for example, I have temperature. Only 2 temperatures, 160 and 180. Basic thing I see is the lower temperature has lower yield, and the higher temperature has higher yield. Right? The overall general trend. Right? Concentration. I can't tell what data point is what in terms of temperature and catalyst, but concentration, I see yields, and I don't see a very general trend going on. Likewise, catalyst, here's catalyst number 0 and catalyst number 1, or catalyst number 1, catalyst number 2. And again, there's no obvious trend with catalyst all by itself. So either temperature might be effective at improving yield all by itself, but the other 2 might have interactions, but as individual parameters, it doesn't look like they're going to affect the yield very much. Well, we can get that much from that, but we can also plot things up using interaction plots. It's similar, but I look at the interaction. For example, there's interaction plot of temperature and concentration with yield as the output, etc. I can generate 3 different ones, and I'll plot them all up on one page. So I'll do this par MFRO 22. That gives me a 2x2 array of graphs, and when I'm all done, I'll switch it back to the normal single graph on a page. All right, so let's do that and look what these graphs look like. When I zoom in, I see the mean of the yield as a function of temperature for 2 different concentrations. Right? So this one is averaging the 2 different catalysts together, so I don't see any of the catalyst behavior. But I do see yield and concentration, these are 2 different concentrations. The legends are a little bit messed up. see if I can fix that a little bit without writing code. If I kind of stretch this up and over and run it again, now sticks my legends in a little bit more readable fashion. So now I see this is the concentration of 20, that's the concentration of 40. So higher temperature is good for either concentration. That's one thing we learn. Here's again yield versus temperature, the two different catalysts. This is the average of the two concentrations. I see that the slope is what's changing when I change catalysts. So temperature raises the yield when I increase the temperature, but it works differently for the two catalysts. Catalyst number 1 better than 0. And here, last one, I look at the mean of the yield versus concentration with these two different catalysts, and I'm averaging the two temperatures together, and I see that the higher concentration actually is producing a lower result, and there doesn't seem to be an interaction between catalyst and concentration. These lines look pretty much parallel to each other. All right, so that's one way to plot. Another way to plot the same thing is using this lattice library, which gives me some other ways of doing these kinds of interaction plots. So let's load up the lattice library and do a plot of yield versus temperature with different catalysts, given the catalyst. All right, so what I have here is catalyst 0 and catalyst 1, and I have yield versus temperature, but rather than showing me the average yield, I actually show you the 2 points. I don't know which concentration goes with each of the 2 points, but nonetheless, I see the same thing we saw before, that for catalyst 0, I get a kind of a gentle slope up, and catalyst 1, I get a greater slope up for higher yields at higher temperatures. Okay? So you can play with different combinations. Here's yield versus concentration for the two different catalysts, for example. Again, catalyst 0 and 1. Instead of showing me the average yield, I'll show you the actual data points. So all of these are interesting ways of exploring the data. Another way is with box plots. I'll show you 3 box plots. I can zoom in to see. And this shows the mean and range of the yield for two different temperatures. So remember, that's going to have both concentrations and both catalysts. So the mean and the range when the temperature is 160, the mean and the range when the temperature is 180. See that no matter what combination of concentration and catalyst I use, we always do better 180 versus 160. And more ambiguous things when I'm looking at yield versus concentration or yield versus catalyst type. So you can study these box plots, box and whisker plots as well. And there's another way to do the box plot where I put multiple box plots together in one graph. For example, I can do, instead of yield versus catalyst, I can do yield versus the combination of temperature and concentration. Combination of temperature, catalyst. Right? So let's take a look at what one of those looks like. And you see I'm showing these combinations, temperature 160 and concentration 20%. So it's labeled temp.conc, and the first number is the temperature, the second number is the concentration. Here's the yield. So these two data points will be the two different catalysts. Now I show 4 different box plots. The higher temperatures are these two higher ones, the lower temperatures are the two lower ones. I can look at the mean and the range, 2 different catalysts. Of course, I don't really know which catalyst is which, just looking at this data. Likewise, I can look at temperature and catalyst. So here's catalyst 0 and catalyst 1, and then the top and bottom of these box and whisker plots will be the 2 different concentrations. All right, you try to look at the data with graphing to see what you can learn from it. Then you do the analysis, and what you want is your understanding of what's going on with the data based on the graphs match numerical values you get when you do your modeling and your analysis. I just discovered this little command, an options command, that allows me to turn off the significant stars when doing modeling, linear modeling, or ANOVA tables. I hate those significant stars. All right, I don't hate them. I think I'm irritated by them. They're annoying. I don't want to see them. So I'm going to turn them off with this little option command. If you're irritated by those stars, you can do the same. All right. How do we analyze factorial data? There's two basic approaches. I'm a regression guy. I do lots of linear regressions. I'm used to thinking about the world in terms of regressions. And for a two-level factorial model or data set, we are only going to be able to do straight line models, linear models. So one way to understand what's going on is to do the linear model, LM, and create a model of yield versus whatever. This allows me to look at effects kind of a bit of it at a time. So for example, I only was cared about the main effects, didn't want to include any interactions. I would do yield as a function of period. Period tells me, give me all the main effects but nothing else. All right. So if I run that and then look at the summary, let's squeeze this back so I can see the summary in more detail. I see that I have the intercept, temperature, concentration, and catalyst 1 as my main effects. It tells me, with no interaction terms, it tells me that the temperature is significant, but that the concentration and catalyst maybe not statistically significant. R squared of my model is 0.84, so I'm explaining 84% of the variance in the data with this, but maybe concentration and catalyst 1 and the catalyst type are not really explaining any of that variance. But that's only when we include the main effects. We'll begin to see that interactions can be significant. So let me do another model. I'll call it model 2, where I do yield as a function of point squared. Point means everything. Squared means give me all the two-factor interactions as well as the main effects. So I will run that model and look at the summary. Now I see temperature, concentration, and catalyst, plus the temp concentration combination, temp catalyst combination, and the concentration catalyst interaction as well. All right. What do I see? I see that, well, my main effects have become less significant, but interaction of temperature and catalyst is very significant, even though the interaction of concentration and catalyst is not. So now I might be thinking that the best model maybe includes the temperature catalyst combination. If I wanted to compare these two models, I could decide if including the two-factor interactions is any significant advantage over including just the main effects. Well, notice our R squared jumped way up to 9996. So I'm explaining almost all the variance with just two-factor interactions. But let's do the ANOVA comparison of the two. This is the partial F test because one model is a subset of the other. And here I see p-value of 0.06. It's marginally better. If I had a 0.05 significance level, I'd say, maybe not. But it is explaining for the variance, but some of that explanation might be due to chance. There's a 0.06 probability of it just being chance. I got this difference in the models. The third thing we could do is to include all the interactions. So this would be a full factorial data set with a full factorial model all the way out to the three-factor interaction. So if I do yield goes as point cubed, that would mean I'm including all the three-factor interactions. And here I can't get any standard errors because, well, I've got exactly the number of parameters to fit as I've got data points. So I will explain 100% of the data. R squared will be 1. Well, that doesn't really tell me how important these three-factor interactions are compared to the two-factor interactions, etc. Another thing we could do would be to search through all the models up to three-factor interactions and then look at something like the BIC or MalloCP or something, as we've discussed in the past, for finding the best subset model. But I kind of think that from looking at the two-factor interactions, that concentration, temperature, and catalyst plus the temperature-catalyst interaction is what's really significant. So I can create a model that only includes those factors, and the equation, the way I do that is with this equation here. So I said yield is a function of concentration plus temperature times catalyst. Just remember, in R, that is not a mathematical equation. It's shorthand notation for explaining what you want. I want concentration as a main effect. I want the interaction between temperature and catalyst. But when I use the multiplication sign, that's telling me I want those two and I want the main effects individually. So I want temperature individually and catalyst individually, plus the interaction. This is just the notational form of the commands in R for creating a formula. All right, so let's do that. I will look at that. I'll run that model and then look at the summary. We'll be able to see exactly what's in the model. The model includes concentration, temperature, catalyst, and the temperature-catalyst interaction. Now I see that every single one of these terms is significant. Right? Concentration maybe possibly not to the 0.01 level, but probably good enough. It's possible that we'll leave concentration out altogether, but it's close. It's kind of on the borderline. But if I left it in, you'd see I'd explain, 99.6% of the variance, just these. So adding the other interaction terms and the three-term interaction is only adding % of the variance or being explained. I think probably we don't need that. You can also look at the values and what they mean and what they tell you, etc. Well, this is how you would look at the problem from a linear modeling perspective, creating a least squares regression of a straight line fit, because we only have two levels. We can also approach the whole problem. Oh, by the way, I can do the same ANOVA. Sorry, the same ANOVA comparing this model to model 2, and model 2 is the one with all the interactions, and all the interactions compared to this one, there's not a statistically significant difference. It's a p-value of 0.3. So I might as well go with the simple model of only one interaction term versus having all the interaction terms present. They're almost the same model. All right, another way to analyze this is with ANOVA, just doing ANOVA properly. So instead of looking at slopes and coefficients of the slopes, I'm going to look at average values of the yield, different combinations. Well, to do that, I have to treat concentration and temperature as categorical variables, as factors rather than as numerical things, numbers that I'm going to use for modeling. So like I did with catalyst, I'm going to, well, first I'll copy the data into a new data set, so I don't have to mess with my original. Then I'm going to change concentration to a pair of factors called 20 and 40, and temperature is a pair of temperatures called 160 and 180. Instead of numbers, those are just the labels for those factors. All right, now I have a data set where I have only factors. And if I do ANOVA, it will simply look at these as if they're categories rather than numbers. So how do I do this? I can do ANOVA, create an ANOVA table for yield versus all the main effects, just like we did before. And if I look at the summary of that, it shows me sum of squares explained by temperature, the sum of squares for the concentration, the sum of squares for the catalyst, and the sum of squares for the residuals, and the F values and P values for each of those. And I see that the temperature is the only one that has a P value less than a significance level that might be reasonable. Concentration and catalyst don't seem to matter. That's the same result, same kind of finding we came up with when we did our linear modeling as well. Likewise, I can do yield versus main effects plus all the interactions using the same kind of formula we did before, and using the ANOVA analysis command or function. I would summarize, and I see going straight to the p-values for the main effects and all the interactions. I see the p-values are the same. Are they exactly the same? Let's see if we can answer that question. I'll just print out the summary of model 2 as well. All right. So here's the p-values. For example, temperature and catalyst was 0.031 when I did the linear modeling, and it's 0.0318 here as well. All right. When I had temperature and concentration, the p-value is 0.2048. I did the linear modeling, 0.2048, just like we had before. So these p-values that we get from the ANOVA analysis are identical to the p-values that we got in our linear modeling. It's essentially the same analysis being done, just being done in a different structure, a different thought process, but we're doing exactly the same kind of modeling work. We should get the exact same results. All right, I can compare those two models together again. Whoops, let's go back to our ANOVA. I can look at all three interaction terms as we did before. Here I can't get p-values because I have exactly the number of parameters as data points. And like before, I could say I had a model of concentration plus temperature times catalyst. So the only interaction term, all the main effects are included. The only interaction term included is temperature and catalyst. That's my fourth kind of model. And here's the summary of that results. And we get the same kind of answers that we got before. All right. Well, if you're more comfortable doing ANOVA analysis, that's great. If you're more comfortable doing linear modeling like me, that's great too. They both give you the same results. I can plot some of the ANOVA results. Here's the residuals for the case of this fourth model. Concentration, temperature, and catalyst as main effects, and the temperature-catalyst interaction included. Here's the residuals, and we don't see any specific trends. I can also plot the QQ plot. Not very many data points, but they all seem to be falling along the slope equals 1 line as well. Another thing we can do is create full ANOVA table. So model.tables, I give it the output of the ANOVA and say I want to show all the means of all the main effects and the interaction terms. I can create that table as well. Here I'll use the model number 2, which included all the main effects and all the interaction terms. I run model.tables. I get the full here table of means. The grand mean, means for the two different temperatures. So for example, at 160, if I average all the data that was collected at 160, I get this mean value for yield, and I 52, and I get 75. Right, same thing, the two different concentrations, the two different catalysts. But I can also create the tables for the temperature concentration interactions, temperature catalyst interactions, and concentration catalyst interactions. Standard errors for the differences of the means. So Lots of different ways of looking at this, but the two main approaches are to do a linear modeling approach, a regression approach, or an ANOVA-based approach. And either one, you can decide what these factors are telling you about how they affect yield. Well, that's the lecture. There's plenty of more to do when it comes to full factorial analysis, partial factorial analysis, etc. I'm not going to go any further in this class. Of course, you could take an entire class on design of experiments. What we'll do next time is move on to response surface modeling. Till then.